Hello everyone. Today I will be talking about the sting of the bullet ant. This ant's sting has been reported as the most painful sting of any animal in the entire world. I decided to make this video explaining the neural mechanism behind why its sting is so painful. The Ponera clavata, also known as the bullet ant, gets its common name because people stung by this ant find the pain comparable to being shot by a bullet. The ant is also called a 24-hour ant because the painful sensation can last for up to 24 hours. Despite the intense pain caused by the sting, it does not cause any long-term damage. In order to have a 50% chance of dying from the sting, you would need to experience 30 stings per kilogram of body weight. Since the average human weight is 81 kilograms, it would take 2,000 plus stings to have a 50% chance to kill a human. The advantage of a sting that causes pain but doesn't easily kill is that an animal that messes with this ant will live to remember the pain and avoid messing with it in the future. The ant is able to induce these painful sensations by using its stinger to inject venom into the target. The main pain-producing component is called Paneratoxin. In this video, I will discuss how Paneratoxin interacts with the pain pathway in animals to produce such intense pain. Before I discuss how Paneratoxin affects pain, I will first describe how pain is normally conducted in our bodies. Our skin is innervated by neurons called nociceptors, whose purpose is to detect damage-inducing stimuli and transmit those signals to the brain. Different forms of pain activate nociceptors in different ways, but in all cases, the painful stimuli induce an influx of positively charged ions into the cell. This positive charge moves along the cell membrane to its terminal in the spinal cord. When the charge reaches its terminal, it triggers the release of the excitatory neurotransmitter glutamate that activate neurons in the spine. The spinal nerve relays these signals to the brain. In the brain, the signal is relayed again through neurons in the thalamus, and finally to the somatosensory cortex. Cortical processing of this information leads to pain perception as well as localization of where in the body the pain is occurring. So where does Paneratoxin act in this pathway? Paneratoxin acts at the very beginning of the pathway by interacting with nociceptors. Normally, after a painful stimulus, channels in the cell membrane open and allow positively charged sodium ions to enter the cell. This positive charge then activates nearby voltage-gated sodium channels. These channels have several components that allow it to exist in three states. When the charge of the cell membrane is low, a component called the activation gate keeps the channel closed, preventing the passage of positively charged sodium ions. When the charge is high enough, a voltage-sensing component will cause the activation gate to open. This allows sodium to enter, and since sodium is positively charged, the charge inside the cell increases further. To prevent overactivation, a component called the inactivation gate moves in and blocks the channel and keeps it blocked. The channel remains inactive until other membrane proteins bring the membrane charge back to normal. This temporary increase in charge around the voltage-gated sodium channel can then trigger neighboring voltage-gated sodium channels, which then proceed to open, allow sodium in, and inactivate. This creates a chain reaction of voltage-gated channel openings and closings that propagates along the neuron all the way to its nerve terminal in the spinal cord. Paneratoxin induces pain by interacting with the voltage-gated sodium channels, particularly the class which is found mainly on nociceptive neurons called Nav1.7. When Paneratoxin binds to Nav1.7, it becomes impossible for the inactivation gate to close. Just like before, pain will produce the opening of ion channels. The influx of sodium triggers the voltage-gated sensor and the activation gate opens. However, because Paneratoxin prevents the inactivation gate from closing, sodium continues to rush into the cell. Since all the channels are affected, the charge of the cell membrane remains high and causes the neurons to continually fire without stopping. This leads to a continuous activation of the neurons in the spinal cord. When the information is relayed to your brain, you will perceive a rising continuous pain since the nociceptors are unable to stop firing as long as Paneratoxin is bound to Nav1.7. In summary, Paneratoxin is the pain-inducing component of bullet ant venom. Normal pain is conveyed via nociceptive neurons in the skin and relayed to the brain via the spinal cord. Paneratoxin induces pain by preventing voltage-gated sodium channel inactivation on nociceptive neurons. This leads to a constant pain signal being relayed to the brain, and as a result you will feel intense pain for a very long period of time until the Paneratoxin wears off. The specificity of Paneratoxin to Nav1.7 explains the non-lethal nature of the toxin. Since Nav 1.7 is primarily on nociceptive neurons, only pain sensation is affected. If it were to instead bind to voltage-gated sodium channels on neurons critical for life, such as those that keep your heart beating or your lungs respiring, it would indeed be lethal. Paneratoxin is not the only venom that induces pain by binding to Nav 1.7. Venom from the Buthidae scorpion also induces pain via an interaction with Nav 1.7. Interestingly, the venom from Thrixopleuma pruriens, tarantulas, blocks Nav 1.7, so bites from this animal will result in pain and sensitivity. In addition, people with Nav 1.7 mutations that result in increased function of Nav 1.7 become hypersensitive to pain, while people with mutations that decrease the function of Nav 1.7 become insensitive to pain. All this together implies an important role for Nav 1.7 in pain. By studying these venoms, scientists have developed drugs that target Nav 1.7 to treat pain disorders. Nav 1.7 inhibitors have shown success in treating pain for people with hypersensitive mutations of Nav 1.7. Thank you for watching. Sources for all the information in this video can be found in the description below.